morning, guys. Two of you are there. Let us wait for some time.
Good morning, sir.
Good morning. I thought I'll take whiteboard class today. Normally, how we used to take initially, but after I set up the board, I understood that my phone doesn't have charge. So, yeah, maybe next time. It's been so long since I thought on a whiteboard after I bought this laptop. So I thought you will also be able to see my face. But yeah, next time. There's a lot of background noise. Let us close the windows. Yesterday we had 7 o'clock class and everybody was there on time. And today is 10 o'clock, and I think people are still sleeping. Yes, if you have if they have your numbers, call them or text them. Yeah, Srivatsan joined. Yes, quickly you can text them and call them. Ask them to join. One more. Sriharini has joined. Okay, I think we can start. Almost all of them. Right, share the screen. Yeah, so hope you remember what all we saw yesterday, right? So we saw majority about nucleophilic substitution. We studied about nucleophilicity. We studied about nucleophilic substitution in benzene rings, right? Which generally doesn't happen, which happens only at extreme conditions, but still we have to provide a mechanism for that. So we provided benzene was the intermediate, right? So we'll move on. We'll move on today to the, say, not the last class of reactions, but still for this particular chapter, this is the last type of reactions, right? So that is electrophilic substitution. Right. Fine. So you will find 99% of times that electrophilic substitution will happen only in benzene ring, right? So you know what are all the different reactions I can have, say nitration, sulfonation, bromination, chlorination, Friedel-Crafts, acylation, all these things, right? So what we have learned, all these comes under electrophilic substitution, right? So now I'll tell you how an electrophilic substitution happens in benzene first, right? Then you the other things are pretty easy, right? Okay, so if I have a benzene ring, right? So let me mark the. So assume that this hydrogen is the one which is going to get replaced. Okay, so fine. So I'm going to have an electrophile. So hope you know what is an electrophile. Electrophile is the one which is going to have a positive charge, right? Okay, so what is going to happen is this electrophile. See, there are two ways of looking at it. Generally, what we do in organic chemistry, or generally what we do in chemistry, is that we make sure that the positive charges doesn't move. It's always the negative charges which is going to move on. Basically negative charge, since I'm saying electrons are the one which we consider to be moving, right? Protons are going to be moving, but we don't consider it much during your mechanisms. But you can either way do it. Say I would tell that this double bond is going to come and attack this electrophile, something like that. Or you can even say that this electrophile is going to attack the double bond. Okay, so now if this attacks, what is going to happen? We will see, right? So you already have hydrogen. Now you have an electrophile. So definitely you see that the pi bond is broken. So this carbon would have had a positive charge, right? And this, right? Okay. Now the resonance structures are going to come into the picture. Now what is going to happen? Now this bond, I can make it come here, right? So now if that happens, I will have a double bond here, and positive charge will be here, and there's a double bond. What happened? Oh God. So there's a double bond here, and now there'll be a positive charge here, and where's the double bond? Double bond is here, right? Okay, and still there is this hydrogen, and your electrophile, whatever is coming, would have been there. Okay, next what will happen? Again, this double bond will come here. I think I'll make some space. So now what will happen? Okay, so now the double bond is here, the double bond is here. Oh, sorry. Right, the double bond is here, and the positive charge is here. So again, hydrogen and your electrophile. Okay, now what is going to happen is this H plus is going to move, and obviously there is a bond here which you see, and that is going to come here, making them so done. So the positive charge is gone because H plus is gone. So you will end up okay, you will end up with a double bond here, 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 and there in this carbon atom, you will have the electrophile. So pretty simple, right? So you can see where we started, right? So we started with a normal benzene ring. So we made sure the double bond attacked the electrophile, or you can say the electrophile attacks the double bond. So now the carbon will have a positive charge. Now the resonance structures, and in the last resonance structure, the H plus is removed and the double bond is made. The electrophilic substitution is complete. Very easy, right? Now the question is, in different reactions, right? How is it that I'm going to produce the electrophiles, right? So you can see, you have seen so many reactions as I mentioned earlier, right? So in all these things, you somehow has to produce the electrophile, right? Say for example, in nitration, you have to produce the electrophile as NO2 plus, right? So all these things we have to do. So we'll see one by one how are we going to produce the electrophile, right? Okay. So now what I understand is, people, since this is going to be an electrophilic substitution, right? Since it's going to be an electrophilic substitution. So obviously, if I have, now you can see that there's going to be positive charges, right, in the benzene ring, in the resonance structures. So obviously, if I have an electron donating group, right, it definitely increases the reactivity of the benzene ring. Is it not? Because it is going to stabilize the positive charge, right? So if I have an electron donating group, right, say you know what are electron donating groups? Say it can be OH, it can be NH2, right? Say all these things, right? So compared to benzene, aniline or phenols will definitely be more reactive towards your electrophilic substitution. But same way, if I have an electron withdrawing group, that will definitely decrease the reactivity for the benzene ring. Say if I have nitrobenzene, or say if I have what is it called, azyl benzene, CH3CO and the benzene ring, right? So benzoic acids, right? All these things will be electron withdrawing groups, so they will decrease the reactivity for the electrophilic substitution. Okay, right. So anyways, now we'll see different reactions, and we'll take we'll see how is it that the electrophile is produced. Okay, say now we'll take an like famous Friedel graphs, right? So in Friedel graphs, what I use is actually a Lewis acid, is it not? Say if you remember certain reactions, now if I have benzene ring, and if I put, say, uh, Cl2 in the presence of, you have to put some Lewis acid. The Lewis acid can be AlCl3, or it can be FeCl3, or it can just be Fe, or it can just be aluminum. Anything is fine, right? So this is going to basically act as the Lewis acid. I'll just write La. La represents Lewis acid, right? So we'll try to understand how is it that, so basically you have to produce Cl plus, the E plus which we mentioned there, right? So somehow you have to produce the Cl plus, so that, you know, I hope the remember, I'm going to get chlorobenzene, not a big deal, right? Chlorine is going to be here, right? The chlorine is going to be here, right? So far we'll try to understand. This is pretty simple. So what happens is, people, the Cl2, right, now when it reacts with AlCl3, right, now we know that AlCl3 is a Lewis acid. So we know what are Lewis acids. Lewis acids will be able to accept a lone pair of electrons, isn't it? So what is going to happen is, this is going to accept a Cl minus, okay, from this, right? This bond is going to, the Cl bond is going to undergo heterolytic cleavage, right? And this is going to accept the Cl minus. And obviously you cannot just easily break Cl bond. So that is facilitated by the presence of this Lewis acid, right? So what is going to happen is, I am going to form the coordination complex. You would have done coordination compounds by this time, so that's why I'm mentioning it. If it was for 11 students, I wouldn't have mentioned. So you will basically have AlCl4 minus, and what is left out? Chlorine plus, and that will attack the benzene ring, and you will form chlorobenzene. The mechanism, as we mentioned, as in the last case. Okay, right? Now, same thing will happen if you go for, say, Friedel-Crafts acylation, right? In that time, you also, you know, you hope you remember what you do. Say you will actually go for CH3CO Cl in the presence of AlCl3. So you know, I'm going to get in this place OCOCH3. Sorry, COCH3, right? So now that, again, if I have it with AlCl3, the same thing only is going to happen. It is going to accept a Cl minus, but this time the nucleophile would have been CH3. I'll just put the double bond down, guys, because I don't have space. CH3CO plus. Again, that would have been the nucleophile, but it's attacking the what is it? The benzene ring. Okay, right? So you'll get acyl benzene, right? What other things? Little graphs, acylation, alkylation. Yes, alkylation. Okay, so alkylation, what do you do? Basically, you go for an RCl, isn't it? An alkyl chloride. Alkyl chloride reacting with AlCl3. Again, it is going to produce my, it is going to accept a Cl minus to form this particular compound, right? Plus, so what will be ending up is with R plus. Again, that would have been the nucleophile. Sorry, electrophile. Sorry, that would have been the electrophile attacking the benzene ring. This is R. Okay, right. What else is there? Filtraves, acylation, chlorination, bromination will be similar. Mm, yeah, right. So these are all the different Friedel-Crafts reaction I can have. So basically, the what you understand from here is that the Lewis base, sorry, so the Lewis acid plays a major role, right, in producing the electrophile, and that electrophile is going to attack the benzene ring, forming, undergoing electrophilic substitution, right? Okay. Now normally say other reactions, if I have say nitration, if I take now nitration, we know what are we going to add. Tell me, what are we going to add, people, for nitration? If I have to get nitrobenzene,
concentrated nitric acid and sulfuric acid.
yes, right. So I use a mixture of two acids, H2SO4 plus HNO3, right? Here, how is it going to happen? Uh, I think it's, yeah, you will have so many complexes getting formed, guys. So basically, from this, you will be getting, now if you put this mixture, you are going to get this NO2 plus ion, and that is going to attack the benzene ring, right? Don't have to worry much about it, right? Okay, so hope you understood. This is actually the overall electrophilic substitution. Right. Now, as I mentioned, coming to reactivities, hope you know, right? So if I have electron donating groups in the benzene ring, right? Say examples can be OH, NH3, and NH2, sorry, NME2, right? And what else? CH3s. I mean, I'll just write R because it cannot be just CH3. Say R, that is any alkyl group, right? So all these things will be electron donating groups. So when you have this compound in any one of the positions, and if you're going to do any electrophilic substitution, I know I'm going to get an ortho or a para product, right? Now, why is because now if you look at the benzene rings, I mean, if you look at the resonance structures of all these, right, you will see that the negative charge is actually going to be only at ortho and para positions. Maybe I'll just prove it. Did we see this, guys? I think we saw this, right, when we studied about when I taught you hydrocarbons, GOC, like gentle organic chemistry. I told you that whenever you have electron donating groups in benzene ring, right, so they will, I told you, I think I took the example of OH or NH2, there'll be lone pairs coming. You can also try the resonance structures. You will see that the negative charge, right, is actually going to be there at para position or ortho position for that matter, right? Now if I have electron withdrawing groups, right, so electron withdrawing groups can be nitro group, right, it can be R CO group, right, or it can be COOH group, right? Any acid derivative for that matter, COCl or whatever it is, anything which has C double bond O, right, is good for me. Even I can even have here, I forgot one thing, OMe, ethers, right? Say they also are electron donating. So anyway, so all these three, and along with all the acid derivatives, will be electron withdrawing groups. I told you they're going to decrease the reactivity of the benzene ring towards electrophilic substitution, and they will always give me meta product. Right, so this and all, I'm just going fast because you already know it, right? So this will always give me meta product. Is that okay? Right, so yes, so that's about your electrophilic substitution. Done. Okay, so now I wanted to spend some time on other little type of reactions. Okay, we'll see what are they. I think now I can close this page. Hope you have, if you have any questions, you can ask me, guys. Anything you saw a question somewhere, like with respect to anything. Okay, so next what we'll see is okay, what will I take? I'll take artificial. Okay, no, there's this important thing we will study about this. Grignard reagent. one of the very important reagents I can have in like in organic chemistry. Okay, so there are going to be so many places. What is it? So many reactions where a Grignard reagent is used. Okay, now first let us understand how do you form a Grignard reagent. Pretty simple. So you should have an alkyl halide, right? So this alkyl halide should react with magnesium to form RMgX. This is what is my Grignard reagent. Pretty simple, right? So now this Grignard reagent, guys, what is it going to do is the question now. So actually this also can be a nucleophilic substitution. So how can I represent it is I can represent it as R minus mgx plus, right? So mgx plus, the whole has one positive charge, and R minus is going to be there. Okay, say for example, if there is an alkyl halide, right? So if there is an alkyl halide Rx, and if I go for this Grignard reagent, say R dash some other alkyl group, R dash mgx, right? So now what do you see? This R minus can act as a nucleophile, right? So obviously when I make this alkyl halides react with Grignard reagents, right? It is actually going to give me nucleophilic substitution. So what is going to happen? The X minus is going to get replaced by R minus, right? So you will get R, R. I mean R dash, if this is R dash, right? So if you have CH3Cl reacting with CH3MgX, you will get CH3CH3. So this is a very good way of increasing the chain length. Now this reaction can be used for your, what is that? Yeah, what is it? Conversions also. If you want to increase the chain length, right? So you can actually use this Grignard reagents with your alkyl halides. Okay, now not only this, so basically this R minus is going to act, R minus is only going to act, but in this case it is what is that, electrophilic sorry nucleophilic substitution, right? Now in some other cases it can act like this also, like when you have uh, when you have carbonyl compounds, right? So when you have carbonyl compounds, say if I have R, I think you should remember this. So when you have methanol, right? If you have methanol, and if I go for Grignard reagent, now it's pretty simple. Now this is an example for nucleophilic addition, guys, right? Actually, I thought I'll take it later, but still some reactions we can see, not a big deal, right? Say now this R minus, right, is gonna come and attack here, and this bond is going to break, right? So now what will you have? I have HC O minus. Basically, O minus would have got OMGX. This MGX plus would have attacked here. So I can write it actually. MGX, OMGX. And in the below, I would have had the R, which is coming from here. And there is one more H, right? Now, if you go for hydrolysis, if you put H3O plus, right? So this MGX will be replaced by H plus. So you will be getting R CH2. There are two hydrogens with a OH, right? So when you have, this is a very good way of converting your carbonyl compounds into alcohols, and with one more advantage that you will be able to increase the chain length depending on what this R is. Okay, right? Lot of times question will come from this. Lot of times you must have known the reaction. Obviously, you would have told you, they would have just told you that when I have formaldehyde, I'm going to get a primary alcohol. When I'm going to have any other aldehyde other than formaldehyde, you will get a secondary alcohol. And if you have a ketone, you are going to get a tertiary alcohol. Now it just depends on what is here and what is here, right? So now instead of this two hydrogens, right? Now if I had two alkyl groups, you should have got your tertiary alcohol. Say if at all I had only one hydrogen and one alkyl group, you would have got a secondary alcohol. But for all the things, mechanism is very similar, exactly same, right? R minus attacks, the bond breaks, then hydrolysis form the alcohol. Is it okay? Right? And like remember that when you have like you can even write as a note, primary, I mean, what is it, acetaldehyde, formaldehyde, primary alcohol, any other aldehyde other than formaldehyde, secondary alcohol, a ketone will give you a tertiary alcohol. Okay, Now, not only here Grignard reagents, there are so many times, there are so many ways. I'll tell you that also. Now, there is a way by which you'll be able to convert a cyanide directly into a carbonyl compound. Okay. Now, how do you go about it? We'll see that. So when you have this RCN, right? So this RCN, if I put it with say Grignard reagent RMGX, right? Now this again will attack this carbon and this would have broken, and the MgX will attack the nitrogen, right? So what will you have? You will have R, C, R dash, I mean the R dash would have attacked. Now you have a double bond, N, MgX. Please come, expecting. Just put a X. Okay, fine, something, right? So I have NMGX. Right. Now this on hydrolysis, when you put H3O plus, right? So this entire thing will be converted to O. Now you don't like, please don't ask me, how is it, sir? I have the entire thing replaced by oxygen. There are series of steps. There are almost like so many steps happening in the mechanism, and eventually this will be converted to R, C, double bond O, R dash. Okay, right? So basically, you cannot convert it to any carbonyl compound. Cyanides to ketone is a huge possibility, is it not? Right? Ketones to, sorry, cyanides to ketone. This is a ketone, RCOR dash. Right? So any cyanide can be converted to a ketone with the help of Grignard reagent again. Okay, now this is also one thing. Is there anything else which I have to tell about Grignard reagents? Mm, yeah, that's it. Okay, with alcohol, oh yeah, one more reaction I forgot. Now they generally say, right, they generally say that Grignard reagents must be stored under anhydrous conditions. You should have studied it, right? When I don't know whether you have seen Grignard reagents in labs, but if at all you would have seen, they would have told you that it should be stored under anhydrous conditions, right? Do you know why?
because it forms hydrocarbons. OH
Exactly,
bonds.
right. Yes, absolutely true. Right. If you have even traces of H plus present, guys, even water is enough, right? Or like even less acidic substances than water, right, are enough to do this. So if you have RMGX, right, even in traces of presence of H plus, now this R minus and this H would form RH. RH basically, if it would have been CH3, this would have been CH4, methane, right? So this should not happen, right? So there are a lot of times, guys, a lot of times this is tested in the JEE exams, right? So they will, if they give you something like this, okay, so students will get, students actually will get this thing. So they will give something like this. Okay, so they have a double bond O. There is a OH here, something, there's a six member ring. Say I have CH, C2H5, C2H5 MgX. Okay, now what generally students will do, right? They will go for the nucleophilic addition. Say they make sure that this one goes and attacks. I mean, right? Say they say that this will come and attack here and all these things, but actually it is really not going to happen. What will happen is I will be getting CH3 as the product. Why? Because you have this OH, right? Now this is capable of giving me H plus. Now no matter you have any other reaction, this is going to be really spontaneous. Okay, so you should get the product as this. Now this reacting with this H plus to form CH3 would have been the product. No other reaction will happen. Okay, so anything, even in cyanides, not cyanides, sorry, even if you have an alkyne, CH triple bond CH, that is also enough for me to make this happen. If you have CH triple bond CH, if you put RMGX, again, you'll get RH, because I know terminal alkynes are little acidic. Okay, anything which can give me little, very little amount of H plus is enough for me for Grignard reagents to react to form your alkanes. Okay, so please be very careful in this. Right, so that is about Grignard reagents. Okay, now next thing what we'll do is we will go for oxidation and reduction. Okay, fine. So now we'll take oxidation first. Okay, so oxidation, now we know what is going to happen, how what and all we can convert to what, right? So generally oxidations will start with alcohols, right? Then you can go for your aldehydes or ketones depending on what alcohol you have, right? And again, aldehydes, if you have, they can be converted to acids, right? Actually, I can see both of them together, right? Say this is oxidation, this is also oxidation, but the reverse one would be reduction. Right, now it's pretty simple, right? So when you have first, we'll see first part. I what is it, aldehydes to sorry, alcohols to aldehydes or ketones. So obviously when you have primary alcohols, they can be converted to aldehydes, right? Secondary alcohols to ketones, and tertiary alcohols will undergo nothing, right? They will not undergo what is that? I mean oxidation reaction, right? They will not undergo oxidation reactions. Okay, now please understand, if you want to just convert alcohols to aldehydes or ketones only, right, you, for this particular purpose, right, you have to use a weak oxidizing agent, right? When you write WOA, represents weak oxidizing agents, right? Now if you put a strong oxidizing agent, right, if you put a strong oxidizing agent, now this will be converted directly to acids if you put strong oxidizing agents. I'll tell you what are weak oxidizing agents and strong oxidizing. I'll give you examples, right? So there's not, you already know, I guess, right? When you have a weak oxidizing agent, just again same thing, if you want to just convert this to this, again a weak oxidizing agent is what is required. And if you put strong or weak, actually I think this can be either strong or weak, actually it doesn't matter, right? It can be either strong or weak. You will end up with acids only. But alcohol directly to acids, you have to put a strong oxidizing agent. Alcohols to aldehydes or ketones, you have to go for a weak oxidizing agent. Okay, right? So again, ketones cannot be converted to acids. Only aldehydes can be converted to acids because of obvious reasons, right? So like ketones will not undergo oxidation. Even if they undergo oxidation, they will not get. They are not going to give you acids for sure. Okay, so these are all the points which you must know. And the example, we'll talk about reduction in a while. Wait. So weak oxidizing agents example can be PCC. Okay, so PCC is pyridinium chlorochromate. Okay, and you have a famous one called Jones reagent. Right, so Jones reagent is very nothing. It's just CrO3. In the presence of a acid, that's it, HCl or H2SO4 or whatever it is. I'll just write H plus, right? So CrO3 in the presence of H plus is a chromic oxide, is what is called as Jones reagent. Okay, do I have anything else? You have, okay, that's it. So these are all the different weak oxidizing agents I can have, right? Now strong oxidizing agents obviously KMnO4, right? K2Cr2O7, potassium dichromate, right? All these comes under strong oxidizing agents, right? Now when I go for reduction, right? Now reduction, See, the mechanism of oxidation is pretty complex. That's why we don't see mechanism of oxidation, but mechanism of reduction is pretty simple, right? Especially when I have certain reducing agents, right? That can be done. Okay, so talking about reduction, guys, again, if you want to convert acid just to aldehydes or ketones, okay, acid just to aldehydes or ketones, obviously you have to use, I can even write it, maybe that will help, right? Acids, I mean, not aldehydes, you can just reduce it, sorry, not ketones, you can just reduce it to aldehydes only, right? So aldehydes only. Now, this can be done only if I have a weak reducing agent, right? And there is only one particular thing which you have to know. There are so many, but you just have to remember this one, dibal H, right? Diisobutyl aluminum hydride. Okay, diisobutyl aluminum hydride. If you want, you can write the full form. They will also represent it. It's a diisobutyl aluminum hydride. So they will have aluminum hydride, and it's diisobutyl, right? So this is what is diisobutyl aluminum hydride. But again, guys, you don't have to remember the structures, nothing, right? So they just give you dipal H. Dipal H is a reducing agent which will convert acids directly to aldehydes, only aldehydes, not further. Right now, if you want to convert acids to alcohols, then definitely you have to go for a strong reducing agent, right? And strong reducing agents are oh, there's one more thing. You can even use NaBH4. Okay, NaBH4 is a weak reducing agent. Okay, strong reducing agent, there is only one thing which you have to know, that is lithium aluminum hydride, LiAlH4. Okay, right? And there, okay, actually, guys, this you cannot use here. I'll tell you where you use it. It's a weak reducing agent only, but this cannot be used here. Okay, so for acids to aldehydes, there is only one thing, that is dibal H, and for acids to alcohol, there is again only one, that is LiAlH4. And what about the last one? The last one is aldehydes or ketones to your alcohols, right? So again, if here I can use either strong or weak, doesn't matter, right? So either strong or weak I can use. So in this case, you can use NaBH4, NaBH4 or LiAlH4. Both of them will give me alcohols only. Okay, so you can write, it can be SRA or WRA. Both of them will do fine here. Okay, either you put dibal H, you cannot you put, you guys. So it can either be NaBH4 or it can be NaBH4. Sorry, LiAlH4 or NaBH4 can be used for conversion of aldehydes or ketones to alcohols. Again, aldehydes will give me primary alcohol, ketones will give me secondary alcohol, just like opposite of oxidation, right? And I want to spend some time on this, and not so much time, just a little mechanism of how it works is what, like this and this actually has the same mechanism. Okay, NaBH4 and LiAlH4 actually has similar mechanism. Okay, now what is that similar mechanism? I'll tell you. So when you have a carbonyl compound, say if you have RC double bond O, say anything, I'll just say a ketone, the mechanism is going to be similar for anything. Okay, or let me take an acid also, not a big deal, right? So this is a carboxylic acid. Now if I put LiAlH4, guys, right? So from the name itself, you can understand it is going to be lithium aluminum hydride, right? We know what is a hydride ion. Basically, this lithium aluminum hydride, sodium, this is called sodium borohydride, right? So all these things are capable of producing this H minus ion. Okay, now this H minus ion will come and attack here, and this bond breaks. So what will you see? You will have R, C, O minus, H, and OH. right? So now if you have another, if you put water, right, maybe this will become OH, right? Now we know two OH groups on the same carbon atom is unstable, so you can remove this H2O, so you will end up with RC double bond OH. Now don't worry, sir, where is alcohol? I'll tell you, there's one more step. Okay, so now this is how the first step is that alcohol, sorry, acids getting converted to aldehydes. Okay, so now we'll see how what happens if I have an aldehyde or ketone in the same process. I think you will be able to predict it very easily. So when you have RC, what happened? Okay, when you have say a ketone, for example. Okay, so this ketone, when I have a H minus coming, again it is going to attack the carbonyl carbon, and this bond will break. So you have RC O minus and a H, and you have another R. So now this will accept H plus. So you will form R CH OH. That's it. So you can see a ketone getting converted to a secondary alcohol, right? So remember that when I have LiAlH4 or NaBH4, they are going to give me hydride ion, and that hydride ion is going to attack the carbonyl carbon, and that's it. And that's how the reduction happens. Okay. Now I want you to write one note, guys. Write a note for NaBH4 for LiAlH4. There's a note. Can you guess what is that? There is one thing special about NaBH4 and LiLH4. What is that? Hmm? Do you know what is special? Or okay, you should. I think somebody should have told you. Any idea? There is one thing special about even PCC, right? PCC, that is an oxidizing agent. Um, what is that? Then NaBH4, LiAlH4, all these things, right? Actually has one thing in common. Can you tell me what is that? Any idea? Okay, I suppose you don't know. Okay, take down the note. For you can just write note for PCC, LiLH4, and NaBH4. Please write a note. Right. So all these three do not affect olefinic bonds. Olefinic means C double bond Cs or C triple bond Cs. Okay. All these three does not affect C double bond Cs or C triple bond Cs. Okay, it is not going to affect any of that. So what I'm trying to tell you is, if I make a, oops, sorry guys, if I make something like this, okay, so if I have a double bond here and a C double bond over here, and say if I put LiAlH4, actually I forgot to tell you there's one more strong reducing agent, I'll tell you that. Okay, so now what will you see is that this double bond will be still intact, and this would have become OH. Oh yeah, correct, this is what would have happened. Okay, right, this double bond would have been staying as such, but the OH, mean the ketone would have converted to alcohol. Right. But the same thing, again, I told you I forgot one strong reducing agent, and the strong reducing agent is H2 in the presence of nickel. Like you remember this, right? We use it for addition reactions, right? So H2 in the presence of nickel again is a very strong reducing agent. So this, if you put, what will happen is that, right? Now double bond is also gone. This will also become OH. Both the things will get affected. Okay, so that is the speciality of your LiAlH4 and NABH4 and PCC also. PCC is for oxidation, but still, right? You can remember that LiAlH4 and NABH4 does not affect your olefinic bonds. Olefinic means C double bond Cs or C triple bond Cs. It is not going to affect that. Okay, now there is one more way also by which I'll be able to use LiAlH4. Right now, that way I can even, since it's producing a nucleophile, that is your H minus, I can even use it in nucleophilic substitution reactions. Okay, now how can I use it? Like pretty simple. Like if you have an Rx, and if you put LiAlH4, so basically you are going to have H minus coming here, and this is going to go out, right? So you will have RH plus X minus, obviously, right? So you can easily see that you can convert alkyl halide directly into an alkane if you use LiAlH4. Or NaBH4 will not work because it is not strong enough, but LiAlH4 will definitely work. Is that okay, guys? Right, so what is the time? Okay, so almost we completed half of the time. So that's it, guys. I have completed majority of the reactions. Okay, almost like there are simple, like there are, say, they are Ulf Kishner, like all the name reactions are left, obviously, right? Reimer Tayman, Ulf Kishner, what one more thing is there? Ulf Kishner, and what is the other reduction? Ulf Kishner's reduction, and other one, Rosen, not Rosen. Oh, I forgot. Okay, anyways, so all those name reactions, aldol condensation, and some other name reactions are important for JEE means, which you wouldn't have studied in your CBSE. All these are only left. So that I think will be taking maybe 3 hours for me to complete that, but that will take up later. We are almost on the verge of completing organic, right? But still, we have to do a lot of problems. That will take care. Okay, so any doubts, people? Anything you want to ask before we move on? Okay. Fine. I suppose there are no questions. So let me bring some problems. We'll do it. Once again. Okay. Okay. Oh, there is one thing in the chat. No doubts. Okay. Fine. Okay. So if you have um, OH, H3PO4 is there. Okay, I forgot to tell you, H3PO4 is also a dehydrating agent, like H2SO4, H3PO4. I even told you anhydrous AlCl3, P2O5, right? All these are dehydrating agents. Okay, bring me the products. Sketch the product. Okay, so by this time you should have got something, right? So can you tell me in one word, not in one word, for me to understand that you understood, or two words maybe I should say. Yes, I'm asking you the two words which will make me understand that you understood. What is the two words? Don't tell me yes, sir. No, that's not, that's not the two words I'm expecting. What is it? Chat. Okay. So okay, fine. So what happens? I have H plus coming. Right now, this H plus is actually going to attack the lone pair on oxygen, right? So I'll just write it down. So you would have had OH2 plus, right? And this H2O leaves. So you will have a carbocation here. Okay, right. Now tell me, guys, can this undergo ring expansion? That was the word I was expecting. Two words. Ring expansion is what I was expecting. Hmm? Can this undergo ring expansion? Yes, no.
Yes, sir.
Right. So obviously what will happen? So you will have this carbon atom is attached to this carbon atom now, but no, I am going to break this bond and I'm going to make it attack here. So a 4-membered ring now is going to become a 6-membered ring. That's what you need to understand. Right. So now I would have had, right, 1 5-membered ring, right? So like, since this is going to be symmetrical, I can just put it like this, two 5-membered ring. And obviously now which carbon would have had the positive charge? The carbon would have had this carbon, or say any carbon which is next to the ring, like this carbon atom would have had the positive charge. If you do it properly, you will understand, right? Obviously this carbon atom which is losing it, so this carbon atom, oh sorry, at the now see this carbon atom, mean, this carbon atom is attached here, right? Now this carbon atom has lost it, is it not? The middle carbon atom has lost it. So you will see that there will be a there will be a positive charge on the bridge carbon atom. Hope you understand why is it there. Again, I repeat, this carbon atom is attached to this. Now, when I broke it, right? But this carbon atom has lost a bond because there is a bond here. That bond is lost. So obviously, that carbon atom is the one, the middle carbon atom is the one which is going to have the positive charge. And obviously, now what is the next step? Removal of H plus, right? Now, removal of H plus, making sure that I have a double bond in the most substituted place, sides of rule. Hope you remember, right? So you will get the product right here. That's it. That's the most substituted place I can have. If I put it either here or here, it is not going to be that much substituted. But if I put it at the right, at the middle, right, that is going to give me the most substituted alkene. So this would have been the answer for this question. How many of you got this? Nobody? No. Okay, no issues. Now you would have got it. Right. Okay, next question. Hmm. So this seems like a very good question. So they're telling I have OH and there's one more methyl group and there is a double bond here. Okay, now I go for HBr. Okay, now I go for HBr. Okay, so let me tell you that the product is not what you expect. Okay, now please remember, like I should have told you this before, but please understand, if you have a chance for a nucleophilic substitution happening within the same compound, it will happen. That's the clue I can give you, right? If I'm again repeating, right? If you can have a nucleophilic substitution internally in the sense in the same molecule, that will be given the first preference. Remember that. That's the product. Okay. Okay, the first step would be addition of HBr to the double bond. So you have to follow Markovnikov's rule, right? So you'll get Br in the most substituted position, and then go for internal nucleophilic substitution. You have a nucleophile inside itself, OH is there. Make OH attack the carbon atom which is having the Br and eliminate Br. That's what you need to do. So remember, like whenever you have this kind of questions, like they want to test you that. Like this is even as a separate mechanism called as SNI. I represents internal. Okay, but it's like if you have practiced little more problems, it's pretty very easy actually to guess these questions. Okay, first step. Okay, let me draw it. So first step is addition of HBr to this double bond. Okay, I have OH. Right, I have a OH and there is one more methyl group. Now if you add HBr, obviously you would have gotten Br here. Obviously H to the other carbon atom. No issues, right? Now what is going to happen? Now you have a nuclear, like now you have a better nucleophile in this compound itself, is it not? That is the OH minus, right? So you will see that this lone pair is going to come and attack here and this is going to leave, right? So obviously you're going to form a cyclic structure, right? So let me count how many membered ring this is this is going to give me, right? So obviously oxygen is going to be along in the ring, right? So we have to count along with oxygen because the oxygen is the one which is attacking the carbon atom, right? So along with oxygen, 1, 2, 3, 4, 5, 6. That's it. These two are the other two. These two are going to be as branches, right? So it's going to be a 6-membered ring along with oxygen. That's what I need to understand, right? So first we'll draw that. So there is an oxygen with a hydrogen, obviously with a positive charge, right? With a 6-membered ring. Right, a 6-membered ring. Now we have to account for the methyl groups also, right? So you can see this oxygen atom has attacked this, oops, right? This oxygen atom has attacked this carbon atom, right? So what I can see, the oxygen atom, the carbon atom which is next to the oxygen atom, again I repeat, the carbon atom which is next to the oxygen atom is having 2 methyl groups. That's what you understand, right? So you can easily see that the oxygen atom is here, right? Either the next carbon atom, either this or this, right, will have 2 methyl groups. So I can even put it anywhere I want. So I'll put 2 methyl groups like this. Okay, 2 methyl groups, and obviously you have a OH plus. So obviously to make it more stable, you can remove the H plus, minus H plus, right? Minus H plus. If you have properly, the structure will come. 2 methyl groups. Done. This would have been the product. Anybody got this? Did anybody get this answer? Okay, I think someone unmuted.
I made a mistake.
Okay, no issues. So you like this, lot of questions will come, people. Please remember that. Okay, so whenever you have this, especially when you have alcohol and your some other nucleophile, say alcohol and your, most probably it will be halides, right? If you want to have it in the same compound, blindly go for this. Blindly go for this. Just go for nucleophilic substitution internal. Okay, right? Lot of questions you will see. Okay, fine. We'll go to the next question. Okay, let me see if you can guess this. We didn't see this, but we'll see whether you can guess the product. Yeah, we know that you know the necessary things. Okay, so it's a double bond, and you have okay. This is CH3COCl, people. Okay, in the presence of AlCl3. What is the product? Let me see. Obviously, you know CH3COCl means I have a C double bond to a Cl, acid chloride. Yes. Let me see if you can get the products. We didn't see this, but still, it's pretty much guessable. You know what will happen if I put CH3COCl in the presence of AlCl3? Don't go for rearrangements, guys. If you're thinking about rearrangements, please don't go for it. Or rearrangements, will it happen? Okay. So you can consider actually rearrangement taking place. Yes, guys, rearrangement is happening. Okay, because you are going to form a carbocation. Okay, so how I don't know whether you would have tried the product. Pretty simple, guys. So you will definitely see from this that I am going to produce right. I am going to produce CH3CO plus. Correct. So this CH3CO plus is going to attack the double bond, obviously, and you have to have a more stable carbocation. So obviously, you have to make sure that this carbon atom is going to attack this carbon atom, so that you will form the double bond here, I mean a positive charge here. So what will be there next? So you will find that you are going to have a C double bond O here with the CH3, right? And this would have had the positive charge, and there is still a methyl group here. This is the secondary carbocation. Correct. Right. Now you see there is a hydrogen here. Right. Now you can see if I do hydride shift, right? If I do hydride shift, that is shifting this to here, right? So now obviously you'll get a tertiary carbocation. It's on the table. Okay. Right. So you will see that you will have yeah, COCH3. Okay, COCH3, and there is this methyl group still there, and the positive charge would have been on the tertiary. Basically, this positive charge would have been here, right? And you can definitely see that it is going to be a tertiary carbocation, more stable carbocation. If I do hydride shift, right? So obviously now you have the Cl minus is left. You can see from the AlCl4 minus, that is going to give me Cl minus, right? So no, entire thing will go, yes, correct. COCH3, methyl group, and a Cl. This would have been the answer. Anybody got this?
Sir, I got it until the previous step.
This one, the carb. That is this step, the carbocation step, or this step? Did he do the rearrangement?
Yes, sir, I did the rearrangement.
Oh, rearrangement. So you didn't know that after that Cl minus will come. No issues at all, right? So after that, I'll have the Cl minus coming from the AlCl4 minus to form the chlorine there. So this is an example for electrophilic addition, guys. As simple as that. Okay, first the electrophile attacks, forms the carbocation, then the nucleophile attacks. The nucleophile is Cl minus. Okay, what is the time? Okay, guys, I think I'll stop with this for today. Actually, I am going to Kerala for New Year, right? So today is my train, right, at 3:30. So I have to do a little shopping, little packing, and all these things, right? So are you guys going anywhere for New Year? Or are you gonna stay at Chennai only with your parents?
Chennai only, sir.
Chennai only. Okay, ask your parents to take you somewhere, right? Maybe if you are like little, maybe next year you'll be in college, right? and what to say, if you're lucky, and if you're not going to stay with your parents, then yeah, then New Year you will actually know what New Year's are, right? Like I don't want to give you the details because I like say fortunately or unfortunately I am your teacher, right? But if not, I'd have told you what exactly it is. But I don't have to tell you. You are smart. You will understand what I'm trying to say. So, anyways, guys, right? So, I think we'll meet this after New Year only, right? So, what is that called? If you wish before, what is it called? Belated, not belated. What is it called, guys?
Advanced.
Okay. Oh, my English is so bad. Okay. Yeah. Advanced Happy New Year, guys. Okay. So we'll meet after the New Year, right? And then I think I am, we'll see whether we are going to continue with the problems or whether we'll start with equilibrium, right? But what I can do in that meantime is I can send you some worksheets if you want for organic, and you can sit and solve. So you can sit and solve. with them. And if you have any doubts, I will be available in WhatsApp. Like, even though I'll be somewhere, I'll be available on WhatsApp. And if you can just click a picture and send me, I'll be able to help you out. And guys, please, the thing is, when it is going to be physical chemistry, it's pretty easy. If you know the formulas, if you know the little concepts, theoretical concepts, you will be able to answer those questions. But you can see, right, you know everything in this, right? You like whatever the problems you have seen today, right? I think it would have given you a very good picture of how questions can be asked in organic, right? A little twist there and there will actually tweak the problem, and the entire product will be different, right? So all these things, how we'll be able to grasp by looking at the question itself is by only through practice, right? But for physical, I would say that even if you don't practice, if you know the formulas and if you have done enough, like good number of problems, it is enough. But for organic, guys, you really have to practice a lot. A lot means a lot. Okay, so let me send you some worksheets. Okay, and then maybe you can try solving them, right? And then whenever you have doubts, you can get back, you can get to me. I think I'll be able to help you out. Okay, I'll post it in the group directly. I'll just post a PDF of the worksheet, right? Or like it might what to say, it might contain questions which we wouldn't have seen, but it's not a big deal. You can always Google it in the sense that you can just see this on reaction with this. That's it. It'll automatically come. It'll tell you the mechanism. It'll tell you the product, how to do everything. It will tell you, right? But that occurring might be little less because we have almost seen everything, but there are still reactions left. Maybe you will be get from that also, right? So I would put maybe around some 100 questions. Okay, so if you can solve all those 100 questions, wonderful, you're set, right? But you can solve how much ever you can in the meantime, till we next meet. I think today is 27th. I'll be back on 2nd. So next week class I will have, definitely, right? Next week, Saturday, Sundays class I will have. So till the time, I think you can do it. Okay, fine, guys. Anything you want to ask?
No, sir.
Okay, thank you, guys. We'll meet again next week, right? And yeah, advance Happy New Year again.
Sir.
Yeah, thank you so much.
Thank you, sir.
Yeah,
Thank you, sir.
thank you.